Hello everyone, and welcome to a brand new series of CPA Turkey webinars. For today, we are pleasure to invite Mr. Shah Kabir to insight us about geothermal energy extraction with wellbore heat exchanger, analytical models, and parameter evaluation to optimize heat recovery. So, to give a little background about Mr. Shah's achievements and expertise, he has over 40 years of experience in the oil industry and 5 years in academia. His experiences include testing and performing forecasting in unconventional reservoirs, pressure and rate transit analysis, wellbore fluid and heat flow modeling, and many aspects of reservoir engineer. He has published more than 130 journal articles and 3 books and contributed to monograph too. His current research interests actually include geothermal energy, extraction by fluid circulation, and carbon sequestration. And currently, he's an advisor at Insidium Technologies. So, if any of our participants have any question to Mr. Shah Kabir, I'm going to forward them after the webinar. So, without any further ado, Mr. Shah, the stage is yours.
Thank you very much. I appreciate that, the opportunity. And good evening to you all. And so we will focus on extracting thermal energy in wellbores. And so in that context, we will have a very little bit of a little piece in terms of what we do in the oil industry and the opportunities that we had missed in the past. So I'll give you a little bit flavor of that. But most of the focus would be how do we bring in our knowledge in the oil and gas industry to harness thermal energy. So what are the motivations? Obviously, we want to minimize our carbon footprints by producing hydrocarbon as well as consuming them in various forms and shapes as we all know it. So that's one of the major viewpoints, that if we bring in another form of energy in the picture with our knowledge and background, then that'll be nice. And we'll briefly, as I mentioned earlier, that we'll very briefly mention how the waste heat can be recovered from producing wells. And the thing is, so how do we go about extracting thermal energy? That'll be the main focus. So it is a closed loop system that we consider in this study. In other words, we typically inject down the annulus and up the tubing. So that's the operational aspect of it. Okay, so we have been working on it for last 3 years or so. So I'll share part of it. And before we do that, get into that, we'll give you a little bit of overview of the global energy demand. And then the direct use and power generation. So this is the item of our interest that we developed some transient heat transfer models for fluid circulation and how we can do that. And we use have come up with the fluid circulation strategy, how we can best do it. Just if we keep circulating fluid day and night, then that doesn't work. So what can we do about it? And we used statistical design of experiments that DOE stands for. And with that, we can learn a lot about which independent variables are consequential to what we are trying to do. I'll share some of that. And then we are in the phase 3 and 4 status, but we will not be able to have the time to get into that. So we will defer it to our next talk. Okay, so here is the overview of ExxonMobil, which came out not too long ago. So as you can see, that OECD countries, the future prediction is that it's going to GDP is going to go up. So as you can imagine, and the same with China going up, and India follows through. And so if I can draw your attention to the figure on the right, as you can see, the in the Asia Pacific region, we have a huge uptick in the middle class, and what that means is when the quality of life improves, that means the energy need for energy consumption goes up. Whereas during this time domain, as you can see, the nothing happens basically in Europe, North America, or Latin America. So Asia Pacific appears to dominate this scenario. And this is the British Petroleum's uh, outlook, among many ways. So what they're saying is that okay, the oil and gas are not going to go away anytime soon, and as you can see, the gas consumption will grow. But the good news is the renewable energy sources are going to grow. So that is encouraging, and this is also shown graphically here. So, so what we'll be discussing today is that a form of renewable energy. Okay, so what's the economic value proposition that the proposed geothermal energy bring to the table, so to speak? So as you can see, if we look at the lenses of average household power consumption, US dominates, and then the European countries follow, and then the big consumers, so India and China, are over here. So much kilowatt hour per month, and so because my background is petroleum engineering, so I want to look at through the lenses of a single well first. And so how many, if we use a single well, how many homes we will be able to feed? So as you can see, is given the current power consumption rate, we can feed many homes in especially India and China. And on the average, we can probably say that okay, maybe 200 homes or less in the developed regions, but the developing countries, we can feed a lot more. So the point I'm trying to make here is that there is a big opportunity to feed the uptick in the demand, energy demand in some of the countries. So what's going on? What are the prospects? So here is a quick prospect evaluation in US and Europe that I'll go through. So if we drill a 7 kilometer well, so there are many hot spots as you can see, and 200 plus is no problem anywhere, but 7 kilometer is fairly deep. But this is just to make a point that there are huge potentials for harnessing thermal energy. So what's happening in some parts of Europe? As you can see that Iceland leads the way, even though the name Iceland may be a little bit confusing, but they have even 300 plus degrees Celsius temperature with only 5 kilometer depth. And then Italy, as you know, it's well known. They have a lot of potential, and also in Hungary, and also obviously in Turkey. Um, so there are a lot of potentials, and then on this region too, uh, there are a lot of thermal energy extraction potential. So we are, what kind of plants we are looking for? So in a typical geothermal plant, so this is, we produce dry steam from the from our geothermal system, and then it goes to turbine, and then we can generate power directly. But if it is flash steam, then it has to go through a, a similar approach as a flash tank. Okay, so and then you put the steam through that, and then you can put the power on the grid. And then we send the liquid down to the injection well. But this would be more common in, except for the high geothermal regions that I just shared with you moments ago, that we have to go through a sort of heat exchanger, and so we are circulating fluid, and it is taking the heat, and then you're generating power. So that's the mechanism. So this is the difference that we have to deal with in most of the countries, unless you happen to be in hotspots around the globe. Okay, so here is some oil reservoir landscape, what's going on, and what are the prospects, if any, in the UK region, for example. So we have 2,200 wells, the oil and gas. And as you can see that if these are the so-called abandoned wells, so they provide the first uh, areas of interest that, okay, we have abandoned wells, can we access them and repurpose for thermal energy extraction? I'll get into that momentarily. And so here's the thing that, okay, we don't necessarily have to generate uh, power per se. If you look at the possibilities of industries that we can feed, from vegetable drying to agriculture and cultivation to sugar refining, you name it, everything under the sun can be done, or we need them for when they need hot water, right? Put it simply. So we have a large demand that we can meet in any society. So we don't necessarily have to generate power per se. So going back to the UK side, so how much power potential can be done from these lot of abandoned wells? So as you can see, there are some prospects here where you're bringing in fluid at over 100 degrees C. Then they can be the targets. But the rest they still provide the potential for hot water, use of the hot water in different industries. What about in Italy? Okay, we have many wells, and then we have a lot of abandoned wells, and so they provide excellent opportunity, given that Italy has inherently high geothermal gradient situation. Okay, so here's just 13 producers and 5 injectors can generate this kind of power, and can heat up so many homes, and so on. So there are a lot of opportunities around. So it's a matter of showing the economic value proposition in a given setting. Okay, so now we'll get into some technical content. So how do we model the thermal energy extraction from by circulating fluid? So we had an article there a couple of years ago. So we considered circulating fluid down the annulus and up the tubing. So that's we are circulating a relatively cold fluid, and then we are bringing in hot fluid. And we also considered, okay, well, how about drilling going horizontally? And that way we can increase the residence time of the fluid, and can we bring in a higher fluid temperature and all that. So they can be all modeled analytically. And so what we found in our initial content, and if this the P50 probability, 50% probability that we can get around 100 degrees C, which is highly desirable for different industries, and not to mention also power. So what came out of that is that horizontal well length is not consequential. Only geothermal gradient and vertical well depth are the key factors. Now, of course, the tubular insulation and all that, they come into play. So this is the design of experiments. We can come up with the cumulative distribution function. And this is the P50 case. That's the 103 degrees came from. And then, so what's going on with the tubing outlet temperature? As you can see, that as we increase the well depth, that is the solution. So if we want to do a simple assessment before you dive into any details, this sort of graphical picture that gives you a quick understanding how deep you have to drill and what temperature you want, and is this economic? And that's the tipping outlet as a function of geothermal gradient. So the big lesson learned is both well depth and the geothermal gradient are the key. If we have high enough geothermal gradient, then we can get very high temperature fluid, and we can generate steam, and therefore power, and put it on the grid. Okay, so there is a follow-up study, and so we found out that, as the saying goes, there is no free lunch. Meaning, if we cannot circulate fluid and expect that everything is fine. So as you can see in this cycle, this is done by Nian and Sheng, and showed that that you have to circulate for 4 months, but you have to shut it in for 8 months. Why? Because we have excessive cooling of the near wellbore geothermal gradient. So 4 months circulation and 8 months shut in. So we use our semi-steady state model, and we are able to replicate that solution. And as I mentioned, why that is happening. So this is the time zero. That's the geothermal gradient. But as time progresses, so after 4 months, if you keep circulating, the temperature drops seriously. Why is that? Because despite the circulation, the heat transfer that needs to occur from the formation into the wellbore begins to deteriorate seriously. So that's the real reason for that. So what's the remedy? How can we fix it? So again, we are circling down the annulus and up the tubing in a closed loop system. So the heat flow cannot keep up with if you keep circulating. So we said, okay, how about doing the stepwise approach, that we step up one step at a time, go up, and then we come down. That way we begin to see that we can control the near wellbore geothermal gradient reasonably well. So this is in hours, but still it shows the decent value proposition. And this is the bottom hole temperature that's occurring in the system. Um, so it's a tentative solution. It doesn't look that bad, or at that when we did this study. So we call it stepwise circulation outcome. So we did the simple analytical solution, analogous to what we do in pressure transient analysis, and we were able to generate, for each case, we got everything on a straight line as expected. And so it's the line search solution in black, and the superposition is in blue. So we got very good one-to-one correspondence of the two. So this is the cycle that we're going through. We are coming down and then going up and so on in terms of geothermal. And this is the outlet temperature profile. That's how it works. So the power generation, it's not a flat response, but as you can see, it's within a decent window, 20 to 30. And you can draw an average line or something to that effect. So it's an improvement over if we are just circulating all day long. You cannot do that. And again, we did the design of experiments, tried to figure out the maximum and minimum circulation rate and the time step that we need to take. So as you can see, the circulation rate, min and max, are the most important variables. And that's the outcome. So roughly your P50 average is, I don't know why this came down. So a little over 2E5 kilowatt hour. And then we found out the tubular diameters also matter for both power generation and net present value. So as you can see that if we enlarge the tubing size, then we have a better outcome as shown in green, and consequent power output. And also shows the NPV value. So it may cost you more for a larger tubular diameter in the system, but you can double your NPV, so to speak. So I'll now briefly share the current outcome, the most recent outcome that we have observed. So we played with many fluids. So the results that I've shared with you up until now has been with water. So, but if you look at the heat capacity, it's much higher than the pentane. So this is when you're circulating down the tubing, as I said, the annulus, and up the tubing. And so it has much better heat carrying capacity, and the outcome is shown here, that you can have a much higher outlet temperature than water. So we did consider many other fluids like CO2 and butane and many others. So overall, what we have found that the pentane appears to work out very well. So in that regard, what we found that, as you can see, that when you do the continuous, so instead, and then you do the intermittent, and this would be the outcome. You can begin to retain the near wellbore geothermal gradient with the intermittent. So by intermittent, we mean, okay, you do one well with 12 hours and the another well with another 12 hours, so to speak. Or you bring in another source of energy. That's what you mean, not stepwise intermittent. So that's the two well configuration. That is so continuous, it will go down as time progresses, and whereas two well, it will remain fairly stable. And we have shown that the economics tell us that, hey, two wells would be just fine. Okay, so here we're showing the all three of them. If continuous, it will go down continuously. And stepwise, yeah, it's an improvement. But if we do it intermittently, meaning either we juxtapose with another well or another source of energy, like solar or wind, you can bring it in, then we can get a much better outcome. So obviously, you would expect a similar outcome in terms of power as well, because your temperature output can remain stable, fairly stable. So we looked at simple economic value proposition plus rigorous. So I'll just show you a very simple uh, outcome. And so if you play with the quote unquote design wells, that means you have the option to drill deeper, or the tubular size can get larger and so forth. So that's what you mean by, so as you keep on the number of wells, as you can see that it grows exponentially. If you have just one or two wells, that doesn't do you any good. But if you want to generate industrial scale power, then you have to drill many wells. And you can do the net present value calculations for design versus abandoned wells. So the abandoned wells are in blue, but the design wells are not there. Yeah, you're investing more money, but the prize is larger. So yeah, it takes the payback period will be somewhat larger, but you are going to get a much better outcome in terms of the power output. So when we talked about repurposing existing wells and all that, so among other attempts which are important here is that their mechanical integrity becomes a big issue. And so, and then when you repurpose, you may have to change the tubing. Because of this, it may be compromised mechanically and so on and so forth. So those costs were not considered in this setting. So again, the cost of electricity matters, and what will be the payback period, as you can see, um, vis-a-vis the NPV. So it's of a payback period is about the same when you increase the number of wells. So scalability becomes an issue. That's the point we are trying to make. Okay, so I have just one example to make a point. This is from the Vault field, and the data has been made available in the public domain. So this has been the oil rate for one well, and this is the corresponding water rate. So as time progressed, especially after 1,000 days, so to speak, the oil water rate went up significantly. But the point here is that because we are producing reservoir fluid, hot water reservoir fluid, relatively speaking, it is bringing in a lot of thermal energy with it. So what we call is the waste heat recovery. So it gives us an opportunity to, with a heat exchanger at the wellhead, you can get harness the thermal energy. So when you were able to do that, here is the total with the oil plus water based on real production, and we found that this is the NPV. And cash flow is that $2,300 a day. But the point we are trying to make is simply this: it's free lunch. I know the field has been abandoned, but if we can retrofit, if we could go back in time, we could have harnessed that thermal energy uh, and making this kind of money. Question is, why not? We're doing it all over the globe. So with that, let me try to summarize what we did. We came up with transient fluid circulation model with different degree of complexity and model formulation. And we find that they're quite flexible in providing the outcome of fluid circulation studies. And the key lesson that we learn is that preserving the initial geothermal gradient or formation temperature is absolutely essential. And we have shown with the analytical solution that we can generate stability in that if we manage our circulation strategy. We cannot keep doing circulating fluid night and day. So we have to I just indicated several steps for doing it. And doing the statistical design of experiment taught us many lessons, what is important. For example, going rather than drilling horizontal well, if you just go a little bit deeper than your existing depth, then that will be far more beneficial because in terms of management of fluid circulation, it will be desirable if we keep the well vertical or near vertical. Okay, so we've shown you one example. We have done many other homework, and we found that the active producers that we have in the oil industry can generate hot water, if nothing else, uh, if not power, depending on where you are. So, and that is literally free lunch. It's we're just letting it go every day. So the wellhead fluid temperature is the key for generating power. So that's why we have to use either directly or indirectly for generating the power. And of course, by the extracting thermal energy, we introduce a green energy in our portfolio. Thereby, we change or minimize our carbon footprint. And finally, I just wanted to make the point that besides the well-known Pacific Rim, so it starts from Alaska to Japan and all the way to the Philippines and Indonesia and New Zealand and Australia and all that on this side, and then on the other side you have California and Mexico and so on, and then come to South America. So besides that, we have many other parts of the world. We have the opportunities for generating thermal energy. So with that, I conclude my talk and thank you for attention.
First of all, thank you so much, Mr. Shah Kabir, for the very insightful presentation. And thank you so much for accepting our invitation, actually, and giving us some of your valuable time.
You're welcome.
So, So to start off, I'm gonna see the questions that came to our comment section. So multiple questions actually came. So I'm gonna start with the first one that came from Mr. Hakkaiden. He says, "Thank you so much for the presentation. The question is, do you have any idea about the potential for thermal power from abandoned hydrocarbon wells worldwide?"
Yeah, so I think as I indicated that if we have, let's say for sake of conversation, the if you have oil industry in Turkey, and Turkey being very receptive to or favorable geothermal system, and same thing goes for the other example I showed, which is Italy. Uh, that can be the serious starting point. And if you have abandoned wells there, I would be curious to go deeper, even with those, to go a little bit deeper, and then try to ensure that we can generate high enough temperature at the wellhead so that we can generate power. Or as I indicated, that if you want to minimize your investment, then you can just generate hot water for different classes of industries that are out there, from agriculture to pharmaceutical.
Thank you so much, Mr. Shah. The second question actually came from Dr. Chandrasekara. You might have known him. So the question is, how much power a single well with bottom hole temperature of 200 degrees, sorry, can generate, and the levelized cost of power?
Um, Very good question, but I cannot give you an answer from the top of my head because we have to uh, figure out the uh, the circulation rate, because that will dictate the volume of fluid that we have at a certain temperature. That will dictate how much power we're able to generate. So, uh, so yeah, we can do those simple calculations, but
Thank you so much, Mr. Shah. There's actually another question from Dr. Chandrasekara. The question is, can we use down the hole heat exchanger to extract heat for power production?
I, I'm, I'm sorry, I don't think I follow that. What is meant by downhole heat exchanger? Um, how is it run and all that? If there is a heat exchanger in, and how deep that is. So all those things will come into play. But if we want to harness geothermal energy, then we have to understand the heat flow mechanism uh, that is in play. So let's say if you are producing fluid from the reservoir, it is bringing in thermal energy without interfering with anything else. So it's not an issue. But when we are just circulating in a closed loop system, then that becomes a challenge. And we have to manage that in a proper way. Some of the steps that I mentioned.
Yeah.
So, so everything hinges on, because there is also Joule Thomson heating that goes on when the fluid comes to the fluid is produced from the reservoir, and
Thank you.
yeah, especially the tighter the rock, the larger the pressure drop, and therefore,
Yeah, yeah. Depends on the structure of it.
correct. Yeah.
Yeah. Thank you so much, Mr. Shah. Actually, I have a question. It's like a general question, but I recently read that Finland is looking to utilize geothermal energy for heating as efforts to cut carbon emissions by the time of 2035. So, what is your thoughts about this subject? Actually, I want to know. I would like
About,
to love to hear your thoughts about it.
are you, can you restate that again? Sorry, I missed
Yeah, yeah, sure.
the
So
top
I
part.
read that Finland is looking to utilizing geothermal energy for heating as efforts to cut all the carbon emissions and become climate neutral by 2035. So I would actually would love to hear your thoughts about this subject. So that's why I asked.
Okay. Yeah. No, I really applaud them. Yeah, I
Do
think
you think
it's
it's like
it's
possible? It's actually possible to get to that point in 2035.
it is possible. I mean, the way technology can evolve, yeah, it can be done. Um, I feel optimistic because I think most of the lessons that we need to uh, learn, not all, but most of them have been learned. But it's matter of executing them, and then the other thing would be the show the economic value proposition. And so we have to probably the quickest way to start this sort of business is to repurpose the wells. I'm not a big fan of repurposing. Let me be very frank about it because of the mechanical integrity issue. We
Yeah.
have studied on that front. So let's say we leave that issue aside, or we can address it. And if it is in a, let's say, in a Turkey or Italy and or favorable geothermal gradient situation, then
Yeah.
that can be the starting point. So have a pilot projects and get the ball rolling, and we can learn so much from that.
Yeah, that's right. Thank you. Thank you so much, Mr. Shah. So, so far, no more question has came to our comment section, and we would like to thank you again for your valuable time and for the insightful information, insightful seminar of yours. Thank you so much, Mr. Shah, and we came to the end of our webinar. So we wish you a very good holiday and get a good days.
Okay, my pleasure. Thank you so much.
We thank you, Mr. Shah. Thank you so much.
Okay, bye bye.
Good evening.